Let's investigate a little bit now an open system. So you understand that in a closed system, you don't have any interaction with the atmosphere, with the surrounding in this case, so you have a certain amount of DIC that is U constant. In a closed system, what is the constant you're going to use is the DIC. The DIC is a various form of dissolving inorganic carbon into the water, and as a function of the pH it will be distributed between carbonic acid, between the PCO2, the carbonic acid, the bicarbonate and the carbonate, and you will shift from 100%. 100% will be your 100% DIC, and then you will have a percentage of this 100% as a function of the distribution of those different species. No adding of the CO2 in your system. But most of the system, most of the natural system can be seen as somewhat an open system. That means you have an exchange with the atmosphere. The CO2 will be most of the time in equilibrium with the atmosphere. So what does it imply? You don't know your exact DIC. The DIC can change, but what is constant is you have your atmosphere with a certain PCO2, and this is more or less constant. It could shift over the million of years in geological history, but as you're doing your calculation, this PCO2 is pretty constant. And so this is in equilibrium with your water. So this will be always constant through the Henry's constant. You know that the amount of carbonic acid formed into a water is proportional to the PCO2 in the atmosphere times a constant, and this constant is as a function of the temperature and the pressure. The pressure will be 1 atmosphere, temperature can change, of course. So this is what you have as with an open system. Again, I'm repeating myself, the closed system, the DIC is constant. For the open system, the equilibrium, the amount of CO2 that is dissolved in the water through the Henry's constant is constant, not the DIC. The DIC is not constant, we'll see that. Let's first consider how much dissolved CO2 you can actually calculate out of the classical reaction we have when you're putting CO2 into water. So we're taking a PCO2, an atmospheric PCO2 of 10 to the power of minus 3.5. I made a slight mistake in the previous video. I put it 10 to the power of minus 3. It is 10 to the power of minus 3.5. So we know that the KCO2, I'm writing that because hopefully with time they will really sink in your brain, is equal to the carbonic acid. I will drop the star here because from now on we will take this H2CO3 as both aqueous CO2 and carbonic acid divided by the PCO2. So now we can clearly see that the amount of dissolved CO2 into the water is equal to the PCO2 times the constant of Henry, or the dissolution constant of CO2 into water. So this is two things that are constant. So this is something that you can calculate. You will know how much of the CO2 from the atmosphere will be in equilibrium with the water, and this is going to be your constant. What is important to notice is this amount is independent of the pH. You don't see any H plus concentration in this equation. So this is whatever pH in your water. If you have an acidic pH, if you have an alkaline water, if you have a neutral water, you will have exactly the same amount of H2CO3 of carbonic acid inside your water. What will change is the amount of other species, bicarbonate and carbonate, but the carbonic acid will be the same. Then we will take the log, because the goal at the end is to make the same plot we did with the Breum's plot for the closed system, but for an open system. Okay, we will want to have the same type of diagram or plot. So to do that, it's easier to plot the log because we want to deal with the pH. The next formula will imply activity or concentration of H+. If you're taking the minus the log of that, you will get a value for the pH. So the log of the concentration of carbonic acid is equal to the log of the PCO2 plus the log of the constant of dissolution of CO2 into the water. First step. Now let's move to the next one. When we're dealing with the concentration of HCO3, what we're going to do now is rewrite all the different equilibrium. The total amount of dissolved inorganic carbon, you can write that by DIC, will be equal to the amount of H2CO3 plus bicarbonate plus carbonate. So you need to express each of those elements, 1, 2, 3. So we need as many equations you need to solve this. We have 4 known, you have 5 equations. So in this case, we just express in the previous slide the composition of carbonic acid as 2 constants. Okay, so we already defined this element. Now we need to define this element. We take the second equilibrium constant, or acid dissociation for carbonic acid, which is going to be HCO3 minus times the concentration of H plus divided by the concentration of the carbonic acid. This, for the first time, you will have your pH, your H plus concentration entering into action here. You can rewrite that as a function because we want this concentration here, K1 H2CO3 minus divided by the concentration of H plus. So this is pretty simple. And we just calculated in the previous slide that the concentration of H plus equal the PCO2 times the constant of Henry, the KCO2. So you can change that and replace it. And now you can write it this way. The concentration of bicarbonate is equal to the Ka1 times KCO2 times the PCO2 divided by the activity. I should write activity, I will just simplify by doing the concentration. And this is, everything is expressed as a function of the PCO2, 2 constant, and the H plus. And this H plus is proportional to the pH. And to make it proportional to the pH, you're taking the log of everything, and that will give you the results of log of the concentration of bicarbonate. New open system is equal to the log of K1 times KCO2 PCO2 plus the pH. Here we go. This is plus the pH because when you're taking the log, pH is minus the log of it. So this is how you can write the concentration of bicarbonate as a function of the pH. This time you see this concentration will change as a function of the pH. This we know this is based on a constant, and this is a pH. Okay, so you can draw a curve and see the evolution of this as a function of the pH. It will increase with increasing pH. You can see that the higher the pH, the higher this value. So contrary to the closed system when everything is constrained in a constant DIC, the DIC here can actually go higher, can increase with time. And you can see here that the more alkaline, the higher the pH, the larger will be the DIC. What we need is to define now the carbonate the same way. To do the carbonate, we are taking the constant 2, the Ka2, which now you should know is the concentration of CO3 2 minus, concentration of H plus, divided by the concentration of HCO3 minus. So you can express the carbonate as Ka2 times the HCO3 minus concentration divided by the H plus. And we just calculate the concentration of H plus here, of H plus, the concentration of bicarbonate here. So you can change in this equation here again, and that will give you CO3 2 minus equal K2 times K1 KCO2 PCO2 divided by the concentration of H plus square. And this is your representation of the concentration of bicarbonate as a function of the pH. If you take the log of it to express as a pH, you will have something like that. CO3 2 minus equal the log of Ka1, sorry, we should put Ka here, time Ka2 time CO2 PCO2, okay, plus twice. So this will increase twice as fast with the pH compared to the bicarbonate, okay? And this is a constant also for a certain pressure and temperature, of course, because those constants are defined by a specific setting of state variable, and this is the PCO2. So now we can actually express everything, what we call the concentration of carbonate or the DIC, can CT equal again the carbonic acid plus the bicarbonate plus the carbonate. So the CT will be equal to the PCO2 times the KCO2. This is equal to that. Now we have plus K1 KCO2 PCO2 divided by H plus. This is this. And we have finally K2 times K1 times KCO2 times the PCO2 divided by the concentration of H plus square. And this is this. So we have this 1, 2, and 3 way of representing that. And everything is now represented with constant PCO2, that is a constant, we know it, and the pH. So you're expressing the DIC as a function of the pH in a known system, pressure and temperature. And if you take the log of it, it's a little bit more complex here, but just to simplify that, you're going to have that to PCO2 times KCO2 multiplying 1 plus Ka1 on H plus Ka2 times Ka1 divided by H plus square, and this can be plotted on the graph. And what is the graph looking like? This way. So this is a plot, a similar plot that we built for a closed system. The closed system was CAP. You know that you had 10 to the power of minus 3, for example, DIC in your system. So this is a plot for an open system with an atmosphere at 10 to the power of minus 3.5 for the PCO2. And this is the pH value here. And this is a log of the concentration in molar. Again, similar stuff. This is a log scale. So we're starting by looking at, for example, this value here, which is, let's put some color here. This value here, which is a constant. This is what is in equilibrium with your atmosphere relative to the Henry's law, not changing the pH. And then you have your increase with time, okay? Because it's, you understand that this is a constant plus the pH. So we'll just increase with the pH. Bicarbonate will linearly increase with a slope of 1, because you always increase with 1 pH unit. You will increase the bicarbonate, and then you will have your carbonate with increase with a slope of 2, because you have 2 pH to increase. Okay, this is your increase with pH. You see that the amount of both species increase with pH, and of course the total DIC is increasing with pH. Here, stable at lower pH, because most of the DIC is under the form of carbonic acid. Then when you're reaching the pKa, the pKa at 6.30, the pKa1 here, at this point you start to have the bicarbonate and the carbonic acid in same amount here. Then you have the pKab here, pKa2 at around 10.33. Okay, in here. At what point here you have an increase the slope of 1 of the DIC, and past this point you have increased with a slope of 2, because you are accumulating both carbonate and bicarbonate. So this is just to explain that first, the amount of carbonic acid created in equilibrium with the PCO2 of the atmosphere is constant. This is a part, this here is a part in equilibrium with the atmosphere. This doesn't change. Okay, this is an equilibrium following the Henry's law. The rest is not, because it will depend on the pH. A more basic water will be able to hold way more DIC, way more dissolved CO2 than a high pH. That's a very important observation. And of course that everything is depending on the PCO2. If you increase the PCO2, and for example take, instead of 10 to the power of minus 3.5, we're taking 10 to the power of minus 2, everything is increasing, you have more, go back to here, this is to this level here, and this is to this level here. You're increasing the entire DIC just by increasing the PCO2. The amount of carbonic acid in equilibrium with the atmosphere increase, and the entire amount of carbonate and bicarbonate increase too. But the value of the pKa1 and pKa2 won't change. They are the same value. So this was a nice little example of two different systems, a closed system and open system. There is a couple of exercises in the assignment. You can actually practice that. It can be pretty complex in some cases, but we will stick with really more simple system right now. When you're going to do more complex example, you're going to use software to model the different phase and different equilibrium you will use for this system. For basic calculation the way you're doing in the exercise, for example, and you can simplify this entire section here that are mainly constant, right? Or as a function of the pH, but you know the pH because you're going to measure the pH. Most of the system you will be able to have a value for this pH. So this can be simplified in a constant called alpha H. So alpha H is 1 plus K1 Ka1 divided by the proton plus Ka1 times Ka2 divided by the proton to the power of 2. So if you're doing the exercise, I advise you to use this example here, which you calculate this value for the parameters that is given in your exercise, and then using this in the following equation. When you want to know how much bicarbonate, how much carbonate, how much total DIC, you can actually calculate if I'm giving you exactly the specific parameters. It's easier, instead of entering every time and doing all the calculation over again, to calculate this alpha H1 and use this formula to calculate the total carbonate or the carbonic acid or the bicarbonate or again the carbonate system here. So use this slide, use this simplification to solve a couple of exercises in the assignment.